Okay, welcome back. Hope you're having a great day. Today, we're going to start a new unit on working machines. In a lot of ways, it's a continuation of the last unit. In the last two units, we talked about forces, acceleration, motion, how things get into motion, unbalanced forces make things move. And now we're going to tie that into how do forces get things done for people. And so the transference here is really, we're going to take it sort of out of the theoretical physics of, what do forces do and unbalanced forces and Newton's laws, and we're going to actually apply it to how do those forces allow people to move things and get things done. So the result of what we get done is work. Now, you need to be real careful about the definition of the word work. In science and engineering, work has a very different meaning than it does in everyday speech. It includes what we think of in everyday speech, but it doesn't include as much, okay? And the definition of work says, work is a transfer of energy that occurs when a force makes an object move in the same direction as the force, okay? And the force is measured in joules, and for work to occur, an object must move. So pushing on a car and nothing changes, it's not work. So if the car is stuck in the snow and you're out there digging and pushing on it and working and working and working, at the end of the day, it's still in the same place because it's stuck. You didn't get it to move. In everyday speech, we might say, well, I did a lot of work. I'm really tired because I've been out there, working on getting the car to move all day, and I'm exhausted. But in science and engineering, there's nothing to measure. The car's in the same place. It's still stuck. So you really accomplish nothing. Now, of course, you got to be careful when you talk to your parents about this. I know that my dad wouldn't have appreciated when I was in the 8th grade if he had been out exerting a lot of effort like that on something. And I was like, well, Dad, actually, you didn't accomplish anything, so you really didn't do any work. He would not have been very happy with me at all. Okay, so the motion has to be in the same direction as the applied force. Pushing on a car and it rolling backwards is not work. So here's an example of this. And, this is a picture of this man, and he's making a great deal of effort. He's trying to get this car that's stuck in the snow to move. And it says, you may be making a great effort, but the car does not move, so you do no work. The distance is 0. So there's nothing to measure. Nothing happened, okay? So one of the things in science and engineering is we need a measurable result. Okay, in other words, something has to happen that we can measure, okay? It has to move. In that example with that poor man, the car, there's nothing to measure. The car there's no result. The car didn't move, okay? So the guy may be tired, and he may have been out there, exerting a lot of effort all day, but he didn't do much work. Pushing a car and it rolling backwards is not work. Okay, now, in the other, in everyday speech, the other thing about this is, like, I might say that I worked all day today, when I get home and I talk to my son, but really I did very little work today in terms of, taking an object and applying a force to it and making it move. Okay, the objects that I move around, maybe the pen, a marker or something, it requires very little force, and I actually don't move them very far. So, when we talk about like measurable work of force being applied to an object and it moving a distance, I don't apply many forces and I don't move many objects very much distance. Like doctors, lawyers, they do very little work too. They don't apply a lot of forces to things. They don't move them a great deal. Sometimes there's almost an inverse relationship to professional jobs and people's salary and how much work they actually get done. Okay, work and energy related. Okay, because energy is transferred to the object doing the work to the object on which the work is done. Actually, work and energy use the same unit. Okay, and the unit is the joule. So the unit for work in the metric system is the joule, and the work unit for energy is also the joule. Okay. And this is really key, that energy is transferred from the object doing the work to the object upon which the work is done. So again, there has to be a transfer of energy. So in order to get the thing to move, the man needed to transfer energy to the object. If the object doesn't move, there's no transfer of energy. It's still in the same place. Nothing happened. No unbalanced force. There's no motion. Okay? Work is done only when a force is applied to an object and the object moves in the same direction as the force. So this is kind of key here too. This is another, deal where you got to be careful, with your new extensive knowledge of science and engineering, about being a smart aleck. Okay, and this picture shows this girl lifting this tub, and only when she's lifting the tub, okay, is it moving relative to herself. Okay, it starts off by her feet, and it's going to move up relative to her waist. So there's a transfer of energy. The tub gains energy when she lifts it up. Okay, it has potential energy now to fall back to the ground. Remember, from elementary school, stored energy. So she's actually adding stored energy to it when she lifts it up. So the definition of work is that the force and the motion have to be in the same direction. So when she's lifting, the force and the motion are in the same direction. When she's carrying the tub, okay, she's not transferring energy to the tub. It's not gaining in any potential energy. Its potential energy is staying the same. It's the same height above the earth. Okay, so when she's carrying it, there's no work done. Okay, so work happens when energy is transferred to the tub. Lifting the tub adds potential energy to the tub. Carrying the tub does not change the potential energy of the tub. So there's no measurable work done to the tub in this case. Now, this is another, like I said, you need to be careful because, somebody was carrying firewood all day long and they were really tired at the end, you'd be like, well, you only did work when you lifted the log. But then when you set the log down, the work was undone because, and carrying the wood did no work. If somebody had been doing that all day and they were really tired, I don't think you would be real excited about your extensive knowledge of science and engineering. Okay, so again, in everyday speech, work has a very definite, different meaning than it does in science and engineering. So I said you can think of it in terms of added potential energy. She adds potential energy when she lifts the tub. She does not add any energy to the tub when she carries it. Okay, now this is another diagram. Remember, these arrows show the direction of the force. They also show the size of the force. So when this lady is pulling on this rope, okay, part of her force is going up, and then part of her force is pulling the sled forward. Okay, so when she pulls on the force, we have this arrow represents her total force. We can break her total force apart into this blue part on the bottom that shows that she's pulling forward, and this pink part where she shows it's part of her force that's going to lifting. This pink part is not work because it has to be in the same direction as the motion of the sled. So she has to be pulling the sled forward. There has to be a transfer of energy as she moves the sled in the same direction. So this part is really wasted effort. So she can make herself more efficient if she made this rope longer and she pulled at a shallower angle. More of her force would go towards pulling the sled forward. Okay, so kind of wanted to summarize all this here. Which part of the woman does force, which does not count. Okay, when the lady pulls, part of her work where she's pulling up doesn't count. The man, does the man do work when he pushes on a stuck car? No, because there's no transfer of energy. It doesn't move in the direction of the force. And when does the girl do work? Only when she's lifting the tub, not when she's carrying the tub, because again, the motion of the tub has to be in the same direction as the applied force. Now, there is an equation for forces, just like everything else in physics and science and engineering. And work equals the force times the distance moved. So again, if the distance moved is zero times even a tremendous force is still no work done. As I said up here, work is measured in joules, and a joule is actually 1 Newton meter. So it's the force that it takes to move 1 Newton, 1 meter. A Newton is the force that's necessary to move 1 kilogram, 1 meter, and distance is measured in meters. So when we plug this into the triangle, work equals force times distance, okay, we're going to put the force times the distance part on the bottom because that's where the multiplied part goes. And then the work goes in the other box. So when we fill this out, it's going to be work equals force times distance. Work will be on the top, and then force times distance will be on the bottom. Okay, so again, we're going to have to be solving some problems. Now, the rate at which work gets done is power. So I can get the same amount of work done quickly, or I can take a long time to do that work. And the difference is the amount of power that we use. So power is the amount of work done in a certain amount of time. So if you walk around the track, okay, you apply forces to make yourself move in the direction of the force. And if you walk around the track, you have your weight, which is the force, times the distance that you move, so you can calculate your work. If you walk, you get that work done in a long time. If you run, you get that same amount of work done. You get it done in less time, so you use more power. And you can actually feel the power, being exerted in your body because, your heart is beating faster and you're breathing faster. So when we put a formula in the triangle, the divided by part goes up and down. This bar represents the fraction bar, so we're going to put work divided by time into the triangle here. And then the third variable is going to go in the last box. And then power is measured in watts. And it's actually after a man named James Watt who invented the working steam engine. Work is measured in joules, and then time, of course, will be measured in seconds, minutes, or hours. Okay. So solving using power using work. These are two-step problems. Okay. This is how much power did the honey badger use if it took him 30 seconds to climb 300-meter tall hill, and he used 50 newtons of force to push up the hill. Okay, so I wanted to add in here, work and energy are also related. So power also equals energy divided by time. Now back to solving this problem. Okay, this is a two-step problem. So you'll need to find the work so we can find the power. Okay, so fill out our triangle, work, force, distance. And we're going to fill out this triangle, work, power, time. So work divided by time equals power. Force times distance equals work. Okay, now let's look at what numbers we know from the problem. Okay, we know we have the time, which is 30 seconds. We have a distance, which is 300 meters. We have a force of 50 newtons. So we can put the time in the time box, which is 30 seconds. We can put distance over here in this triangle, which we know is 300 meters. And it tells us he used a force of 50 newtons. Now, we have enough information to solve for work in this triangle. Over here, we have 3 variables and 2 of them are empty, so we can't do this. But if we find work in this triangle, we can put it into this triangle, and then we can calculate the power. That's why this is a two-step problem. So we know on the bottom, numbers that are next to each other on the bottom of the triangle, we multiply. So to find the work, we're going to take 50 times 300, and that's 1,500 joules. Now we're going to take the 1,500 joules over here because that's the work that the badger did and divide by the amount of time that it took him to do that work. So we're going to take the answer for the work and stick it in the second triangle. And we're going to take the 1,500 joules divided by the 30 seconds. The numbers are on top and bottom, so we'll divide. So power is going to equal 1,500 joules divided by 30 seconds, which is 500 watts. we're going to stop here. I want you guys to answer these questions on your own. We'll pick up here next time when we come back, and then you're going to answer some work problems on your own. I hope you're having a great day, and we'll see you soon.